And now let's see some practical examples of calculations of heat exchangers made with the software EXIST of HTRI. Well, first of all, let's take one exchanger of which we have already made some kind of calculation, and let's give a look to the characteristics that we get from this input file, which is the thermal specification. So, first of all, it is a fixed tube shoot unit, a BEM exchanger. This BEM exchanger has water on shell side and also water on tube side. On tube side, the water, there is hot water, probably processed water. The inlet temperature is 150 degrees, the outlet temperature is 120. This is cooled by 80,000 kilograms per hour of cooling water. The inlet temperature of cooling water is 15 degrees. We do not need the outlet temperature because this is automatically calculated from the thermal balance of the heat exchanger. The water is, the vapor weight fraction is always 0 and 0 everywhere because it's liquid water. The pressure is 9 bar, both on the operating pressure, both on the shell and the tube side. An allowable pressure drop of 1 bar on the shell side and 1 bar on tube side. These are the fouling factors. Probably this low fouling factors is due to the fact that this is processed water while this is cooling water taken from the sea, from river, I don't know. Well, what we have decided, what has been provided in this design. Tube number is not specified. It will be automatically calculated from the shell diameter. The shell diameter you have here is 1 meter. The tubes are 3/4 of an inch tubes, BWG 14, so thickness is 2.11. The length is 6 meters, so standard 20 feet tubes, 6 meter and 96 millimeters. The pitch is 23.813, and it is the tube pitch is 30 degrees, so a triangular pitch. Of course, there is no possibility of cleaning a fixed tube sheet unit on the shell side, therefore a square pitch is useless. Let's see which are the other characteristics. Material is carbon steel everywhere, tubes are also made of carbon steel. Baffles are perpendicular cut, so horizontal cut in this case, since the exchanger is horizontal, and then no spacing has been to tube fine, neither the spacing nor the cut has been specified, but we have specified 5 cross passes. That means 1, 2, 3, 4, 5 crosses of the tube bundle between inlet and outlet. So why this decision has been taken instead of specifying a baffle pitch? Because in any case the program makes some kind of calculation of this spacing and this spacing. Since these spacings are in a certain way obliged by the need of having nozzles here and here. So the dimension of the nozzles will be, in any case, make a constraint to the first baffle pitch and the last baffle pitch, taking also into account that that here you have a tube sheet, you have a tube sheet thickness which is calculated by the software, but of course This is a very rough calculation that has to be later better defined by the mechanical calculation. Now, well, okay, let's make a run and see what happens. Okay, now we have this summary, output summary. Let's check what we have in this output summary. First of all, the first thing that we see on the printout are the pressure drops. 0.4 on the shell side and 0.934 on the tube side. So both pressure drops are within the allowable pressure drop. Shell side heat, the shell side coefficient is 10,000, tube side is 19,000. Very high coefficients, of course. Maybe too high, because we see at the end that we have an over design of almost 80%, which of course is a little bit too much. So this exchanger has a lot of service, more than what is really needed. So what can we do with an 80% over surface? 80% over surface, reduce the tube bundle. To reduce the size of the tube bundle would mean to come out from the limit, specified limit for the pressure drop, because the exchanger has already 2 tube passes. So increasing the number of tube passes or reducing the size of the exchanger would mean to go out with the pressure drop on the tube side. So the best possible solution is to reduce the length of the exchanger in order to reduce the surface without affecting the pressure drop, because if we reduce the length of the heat exchanger, certainly also the pressure drop will decrease. On that, at least the tube side pressure drop. For the shell side pressure drop, we have to see what's the situation, because if we leave these 5 cross passes unchanged, the resulting baffle pitch will be smaller, and therefore the pressure drops will be higher. But here we are very far from the limit. So the best thing is to reduce the tube length. Note, however, that generally speaking, the engineering companies do not like very much to have tube lengths which are shorter than the length they have specified. But in generally speaking, if we reduce the length, cutting 1/2 of the standard tube length of 20 feet is generally acceptable. So what we have to do here, we go in the input, and instead of selecting 6096 millimeter, we select 3048 millimeter, and then we run our exchanger again and see what happens. Now we have reduced a lot of surface, of course, by cutting the tube length to 50% of the original tube length. So we are under surface of about 10–11%. We are within the limits of the shell side pressure drop, but we have a space on the tube side pressure drop. So the idea could be to either adjust the number of passes. That could be a possibility, but take into account that starting from 2 tube passes to go to 4 tube passes would mean to multiply the pressure drop by 8, because generally speaking, when the motion is of of the fluid on the tube side is turbulent, the pressure drop is proportional to the square of the velocity, and therefore just to change from 2 to 4 tube passes would mean to multiply by 4 the pressure drop, and then you multiply by 2 also the length, so it's 8 times. No, this is not a practical idea. So the best thing to do is to increase the shell side in order to accommodate more tubes. So we come back to the input here, and we let me check. Well, 1 meter. Okay, let's try with 4 inches more, so 1100 millimeter, and then we run our exchanger again. Now we are within the specified duty, because the over design is 3.78. The pressure drop is always acceptable. There was also a decrease of the pressure drop on the shell side. Let's check if there is some kind of messages. Shell side inlet condition evaluated, an impingement device is not necessary. ASME section 8 division 1 has been used, so let's give a look to the tube sheet layout. So drawings here to the tube sheet layout. This is the tube sheet layout, which seems reasonable. Of course, there is a lot of space below the inlet nozzle and before the outlet nozzles, because this is reasonable because of their diameter. The diameter is rather high. So the nozzle V square, the rho V square of the inlet nozzle is probably low. If you want to see something more, there is a specific report, which is the final results here, that gives more information. For example, the rho V square shell nozzles, so nozzle rho V square, this is already in English unit, is just a little bit below the specified value of 1500. 1500 is the limit. So above 1500 you need an impingement device. If you want the impingement device in any case, because we are too close to the limit, well, it's not very difficult. If we come back to the input, and then we look at nozzles, impingement here. If we want impingement device, circular plate. So if we are happy with the circular plate, we have just to write here a figure which is a little bit lower, 1400, for example, and then run again the case. We run again the case, well, we go to the output summary. The output summary now, the over design is slightly reduced, -2%. What is the reason? The reason is why probably the number of tubes, and we check drawings, tube sheet layout, you see, in order to accommodate this impingement plate, it was necessary to take out some row or some tube row. Maybe there is the possibility to adjust a little bit the tube sheet layout. We can check. Coming back to the input, tube layout, force symmetrical layout. If we say maybe no here, so we don't want a symmetrical layout, and we run again the case, possibly, well, you see, okay, why this now we have 2% more? Because the layout is not non-symmetrical. We look at the drawing, so it was filled with additional tubes here, while these additional tubes were not provided before because we had specified a symmetrical layout. Now, in this situation, we are at the end of our effort. We just to summarize everything, we look in the report at the TEMA specification sheet. You see, this is the TEMA specification sheet, and we see something more. For example, the transfer rate service is 1,600 and something, while clean is 4,700 and something. So there is a terrific difference between the clean condition and the fouled condition. This is due not only to the fouling factors, but to the fact that these fouling factors, which are reasonably low, but they are high if they are compared to the heat the transfer coefficient, and you see this better in the output summary, which are 10,000 and 17,000. So even low fouling factors will reduce the thermal exchange capability of our unit when it is fouled. So note that in these conditions, having a 2% or also minus 2% of over surface has practically no meaning, no technical meaning. But of course, if you have to prove that your exchanger is reasonably safe from the design point of view, even a 2% should be a plus 2% and not a minus 2%. Well, let's take another case now. We take this file, which is called test 2. Okay, this is clearly a high pressure heat exchanger because it has a D-type channel. The channel, you know, this part of the exchanger, it's a D-type. Moreover, it's not a single unit because you see here we have 4 shells in series. Why they are in series? They are in series because there is a very high temperature cross. You see the shell side in which there is the hot fluid. The inlet temperature is 429, outlet temperature 330, while on the tube side you have a 292 at inlet and 406 at outlet. That means that the outlet temperature of the cold side fluid is 400 degrees, is higher than the outlet temperature of the hot side fluid. This is called a temperature cross. In order to accommodate a temperature cross for multiple pass heat exchanger, it is necessary to put exchangers in series. Let's say other characteristics. If we look at the quality, you have the quality is the percentage of the vapor weight fraction. On the hot shell side fluid we have 1, so 100% vapor at inlet, and 0.9 and something at outlet. So that means that there is a condensation of a very small fraction, less than 10%, but there is a condensation. On the other end, on the tube side fluid, you have 0.165 at inlet, 0.3407 at outlet, so there is evaporation. There is already at the beginning a certain amount of vapor, but the amount of vapor is increasing due to the heat transfer from the hot side fluid. We have to note that the pressure is rather high because you have The inlet pressure here is 130, outlet pressure is 137. Then, other characteristics of this unit, it is a 4-pass unit, and a U-tube, of course, it is a 4-pass unit. It has not specified, an unspecified tube number. There is only the diameter has been specified, 1100 millimeter. And then the tubes are 1-inch tubes. Where it is? It's here, 25.4, 1-inch tubes. Thickness 2.77. Length is 3.1 meter. The tube material is 321 stainless steel, while the remainder of the exchanger is made of low alloy steel, which is a 2.5% chrome steel, which of course is the right steel for that temperature range. Moreover, we have to see that the distance between the inside part of the tube sheet and the first baffle, and the distance from the last baffle to the tube support, this is a full baffle before the bends, in order to support all the tubes before the bends. Those two distances are equal and have been set to 614 millimeter. Possibly somebody has already tried to make some kind of mechanical design of this unit, and therefore these distances are fixed because it depends on the nozzle, on the reinforcement and the reinforcement distances around the nozzle, etc., etc. Then note that these distances must be equal, because if these exchangers are stacked, I don't know if they are stacked the all 4 exchanger, probably only they are stacked 2 by 2, but in any case the outlet of one, if they are stacked, the outlet of the first shell, it must be coincident with the inlet of the second shell, and so on. Therefore, these distances must be equal. Then, let's see how the tube layout is made. How can we look at the tube layout? Not on the summary unit, because to look at the tube layout, we have to select one shell. So, drawings to the 2-dimensional tube layout. So this is the tube layout, and the calculated number of tubes, considering the diameter that we have given, is 796 tubes, which have been the data to be set in order to find this tube layout. Let's come back to the summary unit and then look at the input. In the input geometry, the tube layout is here. Let's see the parameter. So it's a 4-pass U-tube, so it's normal to have the arrangement like that. You have then other characteristics that have been given. Here, force symmetric layout, no, it's not necessary. Force continuous cleaning lanes, this is probably necessary, because if one has fixed a square pitch, this probably means that the cleaning on the outside of the bundle is necessary, but before to make this cleaning, it's necessary to have a continuous cleaning lanes. Align tubes across primary pass lanes is also required, always because of the cleaning on the shell side. Well, okay, in order to check if really this unit is rightly designed, we can run this case. Of course, running a multiple shell in series means that it takes time, because in order to find the right solution, the computer, the program, must imagine the intermediate situation of temperatures between each couple of shells. So if the choice was not right, it has to be repeated many times until the suitable solution is found. Okay, well, look at this value. Unfortunately, this unit is slightly under-designed. It's probably around 1%, but it's minus 1% in any case. So let's check what we can do in order to improve this situation. First of all, we must not look only at the oversurface, we must look at other things. For example, the pressure drops. So this is the summary unit, and so this is the pressure drop of all the parallel shells. So it's 0.47 against 1.8. So there is a space if we want to increase the tube side coefficient. On the shell side also, there is also space, if you like, but what is the deciding coefficient? You have the tube side coefficient is lower than the shell side. It's 1200 against 1400. So the idea is to increase the number of passes. So let's check one more thing. The tube layout is really the tube layout that we have seen before. Okay, let's come back to the input. We take, for example, the first shell, and we look at the drawings. Also, 796 tubes. This is exactly the tube layout we had seen a few minutes ago. Now, if we want to increase the number of tube passes, it's very easy. We come back to the input, we take the summary unit, and we say that we want a 6-pass heat exchanger, or a series of 6-pass heat exchangers. Then we run our case again. Of course, we must be patient, because the intermediate conditions must always be decided by trial and error procedure. So, but I can see here that the coefficients that start to be noted on this plot are always a little bit higher than before, and so we are almost arrived. We must be patient. And finally, we get the solution. So we have a 10% over surface, 10% with a pressure drop, which is always acceptable, 1.27 against 1.8 on the tube side. You see how the tube side coefficient is increased. Now, the first trial with 4 passes, we had 1200, now we have 1800. Of course, there is a space also to increase this coefficient, but let's look at the tube layout now, how is made the tube layout. So again, we must check a single shell, drawings, tube layout. Well, there are always 796 tubes, despite of the fact that now the tube layout is different because we have one more parallel lane. But since we had not specified a symmetric layout, look at this non-symmetric, this tube layout, because if you look here at the number of rows from this side is higher than the number of rows from this side. so it has probably added one more row in the lower part of the bundle, and we have this situation. So this is an acceptable exchanger. However, let's look if there is some kind, so in our report, data check messages, fluid properties, liquid density, liquid viscosity. So this is something that has to do with the input data that it was given at the beginning. So the input data here are curves. So let's look at the summary unit. The summary unit in design, geometry, design, hot fluid properties. You see, this is the hot fluid. So we said before that hot fluid comes in as 100% vapor, and then a small part is condensing. So we have 1, and then 0.9. We have, of course, all the properties of the vapor properties here and the liquid properties here. And if we look at the cold fluid, of course, we have also properties for hot fluid and cold fluid. Look that there is something more. Molecular weight, critical pressure, surface tension. Okay, this is important for boiling or evaporating fluids. This is expressed in dyne per centimeter, and it has been given. The only problem here is that we have a single curve, but generally speaking, we should have at least a couple of curves. Let's look at the wording. Maybe somebody realized, so the program realized this, and so under reports, runtime messages, no runtime messages for the summary unit, but possibly for the shell. Okay, we have a lot of thermal and hydraulic, and incremental pressure has exceeded 90% of the boiling critical pressure, so film boiling, transition boiling. The pressure profiles given for the cold fluid do not cover the operating pressure range, so this is important. But there is nothing to do. If our customer has given a single curve, we must use a single curve. Why do we need at least a couple of curves? Because the curve is not the same if there is a pressure change. So every time the pressure changes, also the curve changes, and therefore also the heat is changed. So you know how the curve is made. The curve are representing the enthalpy. So let's come back to the properties. So input, the summary unit, hot fluid properties. You see that here there is the duty, which is the input, the amount of heat that has been exchanged, so the enthalpy of the fluid. So nothing to do with the single phase exchange, because here we have a change of phase, so it's difficult to distinguish between latent heat and real heat and sensible heat. The problem is that we simply need to know how the enthalpy, so the heat, varies, and how the quality varies. So this is very true for the hot fluid. It is also true for the cold fluid. So we have an increasing enthalpy, while for the hot fluid we have a decreasing enthalpy. So this will give his heat to the other fluid, and so we have this situation. Since the pressure has an influence on this curve, we should need at least two curves, one at the inlet pressure and the other one at the outlet pressure. But nobody knows how really, at the beginning, when starting the calculation, how high the pressure drops will be. So at least we must have a sufficient range of curves in order to be sure that our pressure drop is considered in this range. If we have one single curve, we get a warning, but the calculation, the computer tries always to make a calculation. Let's look again, summary unit, but at each single unit. So input, the reports here. Fill boiling, pressure profiles, we have seen. Number of tubes to meet the TEMA entrance requirement is not the same. Well, it is not a terrific problem. Prevention of tube ends erosion at the inlet needs to be considered in accordance with TEMA. The inlet baffle spacing is less than the calculated minimum inlet spacing. Okay, we said it at the beginning that probably some amount of mechanical design has been already made for this unit. Therefore, these distances at inlet and outlet are already fixed and somebody else has calculated. So this is correct and we should be happy, but there is a small problem. Let's look if first of all at the shell 4. In the shell 4 there is something different. The longest unsupported span of the bundle in the U-bend region and thus prone to excessive vibration. Even with a full support plate, the longest unsupported span should be in the straight portion of the U-tube. Well, okay. If we look at the vibration, so in the report, there is always a vibration report, but I do not see any asterisks here, so we have no problem of vibration. But looking again at this tube layout, I realize that there is another problem. Maybe it's a minor problem, but we must be sure. So what is the problem? Let's look at the tube sheet layout on this shell 4, which is always the same in any case, is equal in all the 4 shells. So we said that on the shell side, where there is the hot fluid, we have a small amount of vapor which is condensing, 10%. So that means that if there is a phase separation, so if the liquid is going down and the vapor stays up, the fact of having a horizontal baffle cut may be a disadvantage, because this could mean that if there is, of course, if the fluid is mixed, so droplets of liquid into the vapor, how it is probably in this case, no problem. But if there is a phase separation, so if the liquid goes down and the vapor goes up, of course the fact of having this baffle cut here means that there is a barrier. So in order to proceed along the exchanger, the liquid level must go up and must be above this baffle cut. So in units of this type, it's much better to have a vertical baffle cut. How can we do? Well, it's not very difficult. We try to let's come back to the input, and we take the summary unit, and we from the geometry baffles, we say that instead of saying cut orientation perpendicular, we say cut orientation parallel. And we run again the exchanger to see what really happens in this case. Of course, we must always be patient. Oh, I see very low. Oh no, now they are higher. So this is the over surface of each exchanger, of each one of the shells. Now we are almost arrived at the end. Okay, now we have the over surface is slightly decreased. The pressure drops are always acceptable. Maybe on the shell side we could increase, for example, we could increase the number of the number of baffles. This is possible because if we look at the drawing of the exchanger, let's no, not on the summary unit, but for example shell 1 exchanger drawing. So you see that this is the exchanger drawing. There are 1, 2, 3, 4, 5, 6, 7 cross passes. You know that with the vertical baffle cut in horizontal exchanger, there is no constraint for the number of baffles to be even. So there is, because if the cut is horizontal, we must have an uneven number of cross passes. But if the cut is vertical, so it doesn't matter how many are the baffles here. So, but in order, before trying to increase a little bit the coefficient on the shell side, let's look if there is any other. So going back in the report, runtime messages here, list one incremental, film boiling, transition boiling, the pressure profiling. I see here this is not nice. Warning, shell entrance velocity exceeds critical velocity, indicating a probability of fluid elastic instability. Shell exit velocity, so this is a problem. How can we solve this problem? There is a very simple, without making major modification, there is a very simple way of, so not on shell 1, but on the summary unit. Let's put, let's analyze a little bit better what happens. So in the shell side, we take the vibration analysis, and you see what is the problem. The problem is here on the entrance and exit in both these parts. We have a critical velocity which is very close to the actual velocity of the stream. So this is causing a risk of vibrations. There is a very simple way, since we have this problem only in the entrance and exit area, and we have not this problem in the bundle, in the other parts of the exchanger. So the simple way is just come back on the input, not in the input summary, but no, let's take the summary unit. Summary unit, geometry, we go to the baffles here, central tube, thickness of tube layout, no, there is something more, supports, variable spacing, supports. Okay, you see these two fields, include the inlet vibration support, include outlet vibration support. What is a vibration support? Which is just a half baffle, which has been set near the nozzle, just to divide in two parts the stream coming in or coming out from or to the nozzle. So the distance, if I remember correctly, the first baffle and the first baffle spacing and the last baffle spacing were equal and were 614. So 1/2 is 307. So we put this vibration support here, and then let's run again this case. Well, we could also have tried to increase the number of baffles in order to increase the performance, so the coefficient in the shell side. However, I mean, maybe it's also useless because we have already a good performance. Let's check if really we still have a positive over surface, and then let's look. So over surface is 8.77. On each unit shell 1, runtime messages, the reports here, okay, tube side monitor, vibration, no problem of vibration. You see how the critical velocity has been increased, and the actual velocity does not change, but the critical velocity has been increased because we have cut in two parts the free length under the nodal. Let's see if there is a problem in shell 4, maybe, but even in shell 4 there is no problem at all. So this is a valid situation. Note, one more note, let's look again at this tube sheet layout. Tube layout, 2D tube layout. Note that with the vertical cut there is also a further advantage. It is to avoid the possible bypass through this large lane, which is due to the bend radius of the inner tube rows. And with vertical baffle, on the contrary, we have not the problem, because this is generally prevented by putting pass lane seal roads or sealing strip pairs. So we could find at least one more thing. We could try one more thing, say to increase the pressure drop on the shell side. So it is a summary unit. We come back to the summary unit, we come back to the input, and we, instead of having 7 cross passes, we put 8 cross passes and see if something is possibly changed. Maybe the fact of having a higher over surface is a better thing, of course, provided the pressure drops remain always under the specified limits. You see, all these attempts can be made very quickly because we are lucky that even with multiple shells, the program runs very, very quickly. Let's see what happens. Still one more patience. Well, okay, we have a small increase of the pressure drop, but no substantial increase of the margin. I would say that the margin is a little bit decreased, even of some small percentage. Why? This is always because of the Tinker method. So the Tinker method, which considered the various streams and takes into account what is the really useful stream, the B-type stream, so the stream which crosses all the baffles. Of course, if the tube sheet is made, the baffle tube sheet layout is made in a certain way, to increase the number of cross passes doesn't necessarily mean that, with the consequence increase of the velocity, doesn't necessarily mean that you improve the coefficient, because maybe you have increased the velocity, but you have also increased the pressure drops, and so maybe you have decreased the amount of the useful stream. So better to come back to the previous number of baffles and leave things like they were before. And now I think I have finished, and I thank you very much for your attention.